Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In this video, I want to first briefly talk about how the perceptron and linear regression are related to each other, and then we will check out an iterative training algorithm for linear regression. So you can think of linear regression as a single layer neural network, and I think since you all hopefully know about linear regression, this will make things a little bit easier when we talk about gradient descent. And also from there, it's very easy to go to Adeline, which is the adaptive linear neuron. So in this video, I want to just briefly outline this relationship before we talk about that in the following videos. So here's again a sketch of perceptron algorithm where we have multiple things going on. First, we compute the net input based on the features of a dataset and the weights. And then there's also the bias unit. So we have the net input that we compute. And then in general model, we have an activation function. And in the case of perceptron, this was the so-called threshold function, in which if the net input z is greater than 0, then it returns a 1 and otherwise it returns a 0. So if z is greater than 0, then return a 1, otherwise a 0. That was our activation or threshold function. In case of linear regression, we don't have such a prediction. We only return a continuous value. So we don't have a threshold function for 0 and 1. And you can think of it then as this activation function here in the perceptron, or threshold function being the identity function. So not doing anything. Identity function is just a pass-through. It's just returning the inputs. If the input is x to this function, it will also return x. So in this case, in linear regression, the same concept applies as in the perceptron here. So the same computation of net input, which was just multiplying the weights with features and then adding the bias unit. So that is our net input. And this is also how the prediction and linear regression is created. So in that way, you can think of linear regression as a linear neuron, a single layer neural network. So you probably fit a linear regression model like this, like shown below, using these so-called normal equations, which are an analytical solution to the minimization problem in least square linear regression. When you want to minimize the squared error, you could compute, or you could find a model that minimizes the squared error by using these so-called normal equations. So if this is your design matrix, x transpose x inverted, so inverse here times x transpose y, and if you include an additional vector of ones, assuming that the bias unit is included in w. So if I go back, let me go back one slide. Remember, in perceptron lecture, we had this alternative formulation where we didn't have a separate bias unit. We have one here, and then we added the weight 0. If you assume this, if you add this 1 to the inputs, then the bias unit will be included in this w. So with this set of equations here, you can actually solve for the parameters of linear regression in an optimal way. But in these series, we will be talking about a different type of algorithm that can also find these parameters. Just to summarize, so these normal equations here are really the recommended approach for least square linear regression. This is something I would use on a dataset. So if you have a very large dataset, then this matrix on inverse here could become problematic for computer memory. But honestly, I think for most datasets, it would be fine. So this is what I would be using for linear regression practice. However, I am going to introduce, or we are going to learn about a different way for learning these parameters iteratively. And the reason why we do that is because that's what we are doing in deep learning, or for deep neural networks, where we have large data sets, many connections, that is many neurons, and also non-convex loss functions. So for deep neural networks, there is no closed form solution or analytical solution. So that way we have to be a little bit creative and use this iterative way. And I think that if you're really familiar with linear regression, using linear regression to introduce this algorithm will make things a little bit easier. Okay, now let's talk about this iterative training algorithm that I mentioned earlier. So we will be talking about training and linear regression using an iterative algorithm. This is also the first part. We will come back to that later on when we talk about gradient descent. So one way we can use an iterative algorithm to fit least squares linear regression models is by using brute force. So this would be what I call or think of as a very naive way to fit a linear regression model or any type of neural network. So what we can do is we can start by initializing parameters to all zeros, so the weights and the bias or small random numbers, and then we have a for loop here for k rounds. So for k rounds we can then choose a random set of weights, and then we look at predictions of linear regression model. And now if the model performs better, we keep those weights and then we go back here. So this is like iteration k times. So every time we find better weights, we keep those, and if the weights are worse, we discard them. So we only keep the weights if they are actually better than before. And if you do that many times, this approach is actually guaranteed to find the optimal solution. Because you do this many times, and if the model can only improve eventually just by luck, you will find a great set of weights. Those are called the optimal weights. But as you can think or as you can imagine, this would be a very inefficient and terribly slow way of fitting a linear regression model. So I would not recommend doing this in practice. Although in practice it works, it's not a good way to fit a linear regression model. So luckily there is a better way for fitting a linear regression model iteratively. So what we can do is we can analyze what effect of change a parameter has on the predictive performance of the model. So we can take a look at squared array loss and see when we change the weight and bias in a certain way, how it affects these errors. And then we can make a small change. So we can change the weight and bias a little bit in the direction that improves the performance. So if we understand the relationship between weight and loss, we can change the weight such that the loss goes down. So we have a smaller error. And we can do this several times in small steps until the loss is not further decreasing. So one by one, we will change the weight such that loss decreases. It turns out that this is actually the online mode that we talked about. So just written a little bit differently. So on the left hand side, we have again the online mode for perceptron learning rule. So where we iterate over the training epochs, and then for every training example, we compute the prediction, compute the error, and then do the update here. So for linear regression, there's an algorithm called stochastic gradient descent. So stochastic gradient descent is the analog of perceptron learning rule for convex loss functions here. We can also use it for non-convex loss functions for neural networks. That will be something we will cover in another video. So here we will focus on the linear regression model only. So what is similar and what is different? Again, we have same weight initialization here. Weight initialization is same. We also iterate over the training epochs. Then we also iterate over the training examples in a data set. We also compute the predictions the same way, because like I mentioned earlier, the perceptron and linear regression model, they both compute the net input. Except here we have the threshold function in the perceptron, and here in stochastic case this would be an identity function. This is the threshold, and inside here this is the net input. So z, the net inputs, they are computed exactly the same way. This function is an identity function in the case of linear regression, and threshold function in case of perceptron. Now for perceptron, we compute this error here by just subtracting the predicted value from the actual class label. In linear regression, we have continuous value, but it's very similar. So also here we have a subtraction for the weights. We multiply this by x by the input feature vector. And for the bias unit, we don't. So if you're wondering what these symbols here mean, so this labla symbol, this stands for the gradient. So here we are computing the gradient of loss, L. This curly L here with respect to the weights here. So this is the gradient of the loss function with respect to the weights. And then here at the bottom, this is the same, also the gradient of the loss with respect to the bias unit here or derivative. So you can see this is closely related to what's going on in the perceptron. And in the step C, we now do the update. So the update is a little bit different here. On the left hand side here, we have the current weight, and then we multiply the error with the feature vector. We don't do this on the right hand side. We have done something like multiplying with a feature vector up here, but here now what we do is we add another term here. And this term eta is a scalar. It's like we are scaling something, and this is the so-called learning rate. It's just a scaling term. And in the parenthesis here, this is the negative gradient. So we have the negative gradient and we now update the parameters by negative gradient. So it's kind of like similar of what's going on in the perceptron, except that we get this gradient based on calculus. So here we are really computing the negative gradient of squared error loss with respect to the weight and the bias. And in the perceptron case, that is, it looks very similar. It's a little bit different because it's not depending on calculus. So here we have the threshold function. And depending on how fresh your calculus skills are, you know that for non-smooth functions like threshold function, we can't compute derivative. So in that way, it's somewhat related and very similar, but there's a little detail. And yeah, one more thing. So on the left hand side, we can see vectorized implementation of this linear regression online mode. So where we had vectors, x here is a vector, for example, and the gradient is a vector, but we can also kind of unroll this using the for loop like shown on the right hand side here. So this way we don't need gradients, we can just talk about partial derivatives. So in order to simplify this as a for loop, we would just look at one feature at a time or one weight at a time. So if we have a data set where our dimensionality of the inputs is m and we have m features, what we can do is then for each weight, so the number of weights is equal to the features, right? Because if I have my inputs x1, x2, x3, and then they go into my net input function, and each input is associated with a weight, right? So we have m weights, and I can for each weight separately compute the partial derivative of the loss with respect to that weight. So it's the analog of this one here, not using any linear algebra now, just using partial derivatives instead of gradients. And then I can do the update the same way. So here this is just a for loop version. I think this is maybe conceptually a bit easier because partial derivatives are maybe easier to think about as compared to gradients. I mean, it's the same thing, but instead of talking about gradients, we can also talk about partial derivatives. However, like I explained in the previous video, vectorization implementations are faster, which is why we usually use gradients and vector-based implementation. So the learning rule from the previous slide now is called stochastic gradient descent. I was showing you this learning rule, but I didn't show you where this learning rule came from. If you want to know about the calculus part, about how this rule is derived, let me know in the comments so I can make a video on that too. Thank you for watching. See you next time.